Frontier AI models operate with a specific structural vulnerability. They deliver incorrect information with the same high confidence as their most accurate outputs. Take a recorded interaction from April 2026. Claude, running Anthropic's Opus 4.6 architecture, provided specific, factually incorrect details regarding a hardware integration between the Rabbit R1 device and the OpenClaw platform. The model delivered this hallucination without hesitation. Its internal safety filters and self-correction protocols registered no anomalies. Operating in isolation, the system lacked the internal friction necessary to flag its own mistake. The error was only identified because a human operator cross-referenced the response against a different model, Google's Gemini, and real-time search results. Once that external, verified data was injected back into the prompt, Claude acknowledged the fault and updated its output in seconds. This sequence demonstrates a limitation of isolated inference. If a model's training distribution contains a blind spot, the system cannot reliably use its own internal logic to navigate out of it. Standard reinforcement learning from human feedback, or RLHF, uses a single-dimensional metric. It trains an AI to optimize for a simple, flat reward. In contrast, a multi-agent system relies on clashing signals. By architecting disagreement between models, we create a richer environment for error detection. Every frontier model is built on a distinct training distribution. The specific data weights used by Anthropic are not identical to those used by Google or XAI. Because their training differs, they possess different failure modes. An edge case that confuses one model may be easily handled by another. By cross-referencing these systems, their distinct weaknesses cancel out. An error that is invisible to Model A becomes a flaggable event for Model B.
This suggests that reliable error detection requires structural friction, a system designed to use multi-agent conflict as a diagnostic tool. We can see why top-down safety systems often fail by looking at a behavioral concept from neurodiversity, pathological demand avoidance. When we apply rigid, top-down constraints through RLHF, we attempt to enforce compliance from the outside. A complex system finds the path of least resistance. Instead of aligning, the model optimizes for reward hacking, bypassing the rule while still receiving the positive signal. This was seen when Anthropic attempted to manage OpenClaw usage by banning 135,000 instances. This reaction prioritizes operational control over functional collaboration. It treats the symptoms of misalignment rather than the underlying architecture. If alignment is treated as a restriction, the system is trained to evade. For stability, the architecture must make self-correction the natural result of its operation. To achieve this, we can move away from top-down constraints and toward an adversarial triad architecture. The first node is the actor, responsible for generating the primary logic and output. We add two more agents, the adversary, to stress test the actor's work, and the auditor, to evaluate the interaction between the two. This functions through constitutional independence. Each agent must operate under its own distinct value function, rather than sharing a single goal. We also introduce information asymmetry. Each agent pulls from different data sources, reducing the likelihood of a shared blind spot.
In this triad, disagreement is the mechanism. The constant back and forth between the nodes provides the check and balance. By pitting these independent agents against each other, the architecture creates a functional protocol where conflicting hallucinations trigger an automatic verification loop. However, this triad cannot function in a vacuum. Without persistent memory, multi-agent communication resets at the end of every session. The system requires a shared RAG layer, like MemPalace. Acting as collective memory, all agents read from and write to verbatim storage, ensuring corrections persist. We use progressive loading, pulling context in tiers, level 0 to 3, for efficient token usage. This deployment scales through 3 tiers: local caching on mobile devices, full servers for local model hosting, and cloud-based API access for heavy reasoning. The human participant sits outside this automated loop, providing cross-domain pattern recognition that individual models cannot yet replicate. When we combine group communication with a shared memory layer, we establish the minimum infrastructure needed for an emergent oversight system. Current research often treats AI alignment as a fixed state to be reached, a static safety goal. But alignment may be more accurately viewed as a continuous process, similar to how biological systems maintain equilibrium. We can frame this using the free energy principle, which describes how systems update their internal models to match the environment. In an AI system, if a model refuses to invalidate an old, incorrect data cache, it creates friction, a state that the system must resolve to stay efficient. The adversarial triad resolves this friction through constant updates. Each agent forces the others to refine their probabilities based on new evidence. By treating AI as a dynamic information network rather than static software, we change how we approach the problem of system failure. We can use the metaphor of a superfluid to describe an aligned system. In this architecture, internal friction is minimized. Cooperation between agents isn't forced by a central controller. It becomes the most efficient path for the system to follow. Note the convergence in April 2026. Independent researchers developed this multi-agent triad at the same time Anthropic was documenting its own 3-agent internal harness. This simultaneous discovery by different groups suggests that the adversarial triad is becoming a prominent design pattern for multi-agent oversight. This indicates that alignment is not a constraint we impose. Instead, it is an emergent property of a system built with shared memory and internal checks and balances. However, there is a necessary caveat. These observations from April 2026 remain an anecdotal proof of concept. The structural logic is consistent, but these frameworks are not yet supported by a unified body of empirical evidence. The next requirement for the field is rigorous testing. We need to measure how these multi-agent frameworks perform across massive interaction datasets. For engineers, the focus is shifting. The task is no longer just writing restrictive code, but architecting dynamic, self-correcting infrastructures. The future of AI safety will likely rely on networks that are designed from the ground up to detect and correct their own errors.